Okay, let's dive right into this explainer. Think of this as your personal exam survival guide. It's basically a masterclass designed specifically to rescue those lost points on your upcoming physics final. We're going to systematically break down the absolute core measurement principles that serve as the foundation for literally everything else you do in physics.
Now, let me ask you, are you losing easy points on your physics exams because of rounding errors or, messy units? Look, I have absolutely been there. And as a mentor, I see these exact same frustrating mistakes every single semester. You do all the complex algebra perfectly, you completely understand the core physical concepts, but then bam, you lose half credit on a question just because of a trailing zero, a rounding error, or mismatched units. It is incredibly frustrating. But the really good news, it's also completely preventable.
So here is our study guide syllabus. 1. The modern SI unit standard. 2. Significant figures and pitfalls. 3. Arithmetic, logic, and rounding. 4. The dimensional consistency principle. And 5. Deducing unknown relationships.
Section 1. The modern SI unit standard, the universal language of physics. To really appreciate our modern system, just take a look at this timeline of the absolute chaos scientists used to deal with. Pre-1971, different countries were using entirely different systems. You had the CGS system using centimeters and grams over here, while others used the FPS British system of feet and pounds over there. Imagine trying to collaborate globally when you can't even agree on how long a meter is, right? Standardizing the SI system under the BIPM in 1971 and then revising it in 2018 with fixed constants was completely necessary to avoid global scientific confusion. It finally gave us a universal decimal-based system.
Now, there's a fundamental difference within the SI system that you need to grasp: base units versus derived units. On the left, base units act as the fundamental, independent building blocks of the physical world. Think of them like Legos. You can't break them down any further. On the right, derived units are just combinations of those base units, multiplied or divided together to describe much more complex things, like velocity or force.
And here they are, the 7 fundamental base quantities. We've got length in meters, mass in kilograms, time in seconds, electric current in amperes, temperature in Kelvin, amount of substance in moles, and luminous intensity in candelas. You have to memorize these. They literally form our international standard and serve as the absolute foundation for every single derived counterpart, like newtons or joules, that you're going to see on your test.
Now, there are 2 really special exceptions you need to know about: plane angles, measured in radians, and solid angles, measured in steradians. Think of a plane angle kind of like slicing a 2D pie, and a solid angle like cutting a cone out of a 3D watermelon. They're defined as ratios, an arc length divided by a radius. Because you're basically dividing a length by a length, the units just cancel out. Therefore, these angles are incredibly unique because they are fundamentally dimensionless ratios.
Section 2. Significant figures and pitfalls. Avoiding the trailing zero trap. Okay, let's rapid-fire the strict rules of zeros. All non-zero digits, they're significant, obviously. Zeros trapped between non-zero digits, yeah, they count. Leading zeros, they literally never count. They're just holding the decimal place. Now here is the trickiest part: trailing zeros. If there's no decimal point, like in 12,300, those zeros do not count. But if there is a decimal point, like in 3.500, they absolutely do count. Remember, significant figures indicate the actual physical precision of your measuring instrument. They aren't just random math rules. We can actually completely bypass all that ambiguity by linking SI prefixes to decimal powers. Check this out. Converting 4.700 meters to millimeters gives us 4,700. Suddenly, a measurement with 4 sig figs looks like it only has 2. But by packing these numbers into scientific notation using decimal powers, it acts like a suitcase. The base number stays exactly the same, 4.700 times 10 to the third millimeters. All that ambiguity vanishes, which reduces calculation errors immensely. It's a total game changer.
Another massive benefit of scientific notation is the order of magnitude, represented by that 10 to the power of b. The Earth's diameter is on the order of 10 to the 7th meters, while a tiny hydrogen atom is 10 to the negative 10th. You can use this to quickly estimate and verify if a calculated answer is physically reasonable. If you calculate the size of a molecule on an exam and get 10 to the 5th meters, you immediately know you've made a huge mistake before you even hand it in.
So, the absolutely crucial golden rule here is this: a mere change of units cannot change the number of significant figures. Never, ever let a simple unit conversion, like jumping from kilometers to millimeters, artificially inflate or deflate the precision of your original measurement.
Section 3. Arithmetic Logic and Rounding. The rules of engagement for calculations. All right, here is your step-by-step logic for rounding operations. For multiplication and division, your final answer matches the input with the least significant figures. Simple enough? But for addition and subtraction, the rule shifts. You match the input with the least decimal places. And step 3 is vital. So many students mess this up. In complex, multi-step physics problems, never round prematurely. Always retain one extra digit in your intermediate steps and only round off at the very end.
Let's actually walk through these exact sample calculations together. When we divide mass by volume to get density, the mass has 4 sig figs, but the volume only has 3. So our final density of 1.69 must be restricted to 3 sig figs. But when we're subtracting lengths, we don't care about total sig figs, we care about decimal places. Both inputs go to 3 decimal places, so our result, 0.003 meters, also goes to 3 decimal places. See? Distinct physical logic for distinct operations.
Now, when you combine measurements, you've also got to combine their uncertainties. If you multiply a length and width that both have a plus or minus 0.1 centimeter uncertainty, those errors actually stack. Using combination of errors rules, the final area isn't just a perfect 164. It becomes 164 plus or minus 3 square centimeters. Ensuring your final answer reflects these true experimental limits, that shows true mastery of the material to your professor.
Section 4. The Dimensional Consistency Principle. Literally the ultimate cheat code for checking your work.
The absolute physical reasoning behind this principle is super simple. It's the classic apples and oranges analogy. You can multiply different dimensions together to create a new derived unit, absolutely. But adding or subtracting, you can only add identical dimensions. You can't add velocity to force. It breaks the universe's rules. Just like you can't add 3 apples to 5 oranges and get 8 apple oranges. It's just physically impossible.
So let's pose a classic exam question to test this concept. Say you derive the kinematics equation for distance on a test, x equals x naught plus v naught t plus 1/2 at squared. But you're kind of stressing and aren't sure if you remembered it correctly. How do you check it? Well, you test its dimensional consistency.
Here's how we do it. First, distance x and initial position x naught both have the dimension of length, represented by L. Second, velocity times time. Velocity is length over time times time. Those identical time units can be algebraically canceled right out, leaving us with just length. Third, acceleration times time squared. Acceleration is length over time squared multiplied by time squared. Again, time cancels out entirely, leaving length. So our result is length equals length plus length plus length. Because every single term perfectly reduces to the same dimension, we've just proven the equation is consistent.
Section 5. Deducing unknown physical relationships. Reverse engineering physics formulas.
Okay, let's do a masterclass derivation for a pendulum's period t. We go on the offensive and guess it depends on length L, gravity g, and mass m raised to unknown x, y, and z. We apply our dimensions. Time equals length to the x times length over time squared to the y times mass to the z. By mathematically matching the exponents on the left and right sides of the equation, we find x equals 1/2, y equals negative 1/2, and z equals 0, meaning mass doesn't even matter at all. Plugging those exponents back in reveals the true physical formula. Period equals a constant k times the square root of length over gravity.
But wait, what about that k we just saw? Well, this brings us to the dimensionless trap. Dimensionless constants are pure numbers, like 2 pi or ratios. More importantly, the arguments of trigonometric functions, logarithms, and exponents must absolutely possess 0 dimensions. Why? The physical reasoning here is that an exponent is essentially just a set of instructions counting how many times to multiply something. You can't multiply a base by 3 meters, that's nonsense. It has to be a pure dimensionless number to make physical sense.
Which leaves us with this final, kind of provocative question. If your equation passes the dimensional consistency test, does that guarantee it is exactly correct? Well, the answer is no. While a wrong dimension guarantees your equation is incorrect, a dimensionally correct equation might still be missing an essential dimensionless constant, like a 1/2 or a 2 pi. Dimensional analysis is a remarkably powerful tool, but it doesn't do all the work for you. Always double-check your logic, remember your significant figures, and you will absolutely crush your physics final. Keep practicing, and I'll see you in the next explainer.